John Verboncoeur de Michigan State University. Espero que sea de interés particular para los estudiantes en lo que se refiere a simulación numérica, especialmente para los casos de aplicaciones en la industria. So please go ahead.
Thank you very much, Julio. It's my pleasure to be here today. I'm going to talk about several different things. In particular, I'll talk a bit about the simulation of plasmas using particles, and I'll show a set of codes. These are free codes that you can get on the internet, and I'll try to show them through a virtual machine here. They run under Unix. The virtual machine works fine, except I'm not sure it's compatible with the display, so hopefully we'll get that to work, but we'll do that after we do the initial presentation. So, first, because this is a Nuclear and Plasma Sciences Society Distinguished Lecture, I have to show these slides, which are the propaganda for NPSS. And so the notion here is just a few of the details about the benefits of membership of NPSS. And so you can see some of those benefits there include things like access to IEEE journals and reduced conference registrations and so forth. But I think some of the more important benefits are things like opportunities for leadership. So for example, you have sort of a range of leadership opportunities that involve, for example, working with technical conferences, working with publications, being a journal reviewer, being a guest editor, senior editor, associate editor, and so on, at all the different journals, as well as administrative positions. For example, I'm the past president of the NPSS, and so this involves 8 different technical communities which run 8 conferences per year and a budget of about $5.5 million per year. And so about 3,000 members, about 6,000 total attendees at the conferences across that portfolio. And so the NPSS is just one part of the IEEE. There are 46 societies and councils in the IEEE and about 420,000 members worldwide. About 55% of the membership is outside the US, so it's become increasingly international, and in fact it's becoming more so going forward. So lastly, just a few of the Nuclear and Plasma Science Society publications and conferences, just so you can see the full range of different things, which I think interact well with a lot of the topics that we're seeing in the recent talks in the last couple of days. So, and we don't have a membership booth for bureaucratic reasons, but normally we would have a membership booth here. You can see both the conferences and the journals, and some are overlapping a lot of the work that we've been talking about. So let me then, without further ado, go to the technical part of the talk. And so I'm going to talk a little bit about the plasma simulation scheme, but I'm going to talk about that only in a very basic way. I'm going to talk about the fundamentals. So that second half of the talk, which are really advanced methods, I'm not going to go through that because that would become an hour-long talk. And I'm hoping to spend about the second half of the talk running some simulations. So hopefully I'll be successful in getting those to work. The machine's being a little finicky with this display. Anyway, so I'll talk a little bit about the background of particle simulation, how we got here, and then I'll talk about the basic methods by which it works, and then I'll show a set of codes that you can actually download from the internet, including the source code is available as well, and there's hundreds of examples that you can run and modify for your own purposes. These codes are used, the codes that I'll talk about today originally came from the Berkeley code suite. I was at Berkeley in the Department of Nuclear Engineering for about 25 years before I came to Michigan State 6 years ago, and so moved all those codes to Michigan State with me, and so we have a big and growing group working on these codes and distributing them worldwide. There are about 350 publications in the last decade or so which cite these codes, and there are many more which unfortunately don't cite the codes, but those publications are by folks outside of our group, so people internationally are using this both in the classroom and for research. So first, a little bit about the motivation. Why should we be interested in particle simulation? Well, about 99% of the matter in the visible universe is in the plasma state. And I like to tell my solid state colleagues that the other 1% is just a condensed plasma. So it's waiting to become a plasma. Next, kinetic effects are very important in a lot of practical phenomena and devices. And so the particle model allows us to simulate a general distribution function. It doesn't require us to make, for example, an approximation for a Maxwell-Boltzmann distribution or something similar. It lets us have a time and spatially dependent distribution function. And it also allows for nonlinear effects. Those nonlinear effects can be very important in a lot of instabilities and other important physical phenomena. It also allows us to treat relativistic effects so that we can handle relativistic beams, astrophysical phenomena, and so forth, where relativity becomes very important. Space charge effects are another important aspect that are captured here, and in particular, collective effects are well captured. Most of the models that we'll talk about are self-consistent. There are times when we actually have to use, for example, phenomenological models where, for example, if we're looking at a plasma interaction with a surface, many of the surface physics coefficients come from experimental measurements and tabulation rather than from doing basic physics on, for example, a molecular dynamics scale, just because those time scales and space scales just become too great for our current generation computers to be able to handle. And then finally, we'll try to use as few approximations as possible. There will be times when we have to use some approximations. There are some disadvantages to particle methods. Those include statistical particle noise. And so the noise in a system is proportional to the inverse of the square root of the number of particles we use. So that means that if we want to get half the noise level, we have to quadruple the number of particles. And so that's obviously not a very favorable scaling with respect to noise. So that's one of the biggest challenges. Now, there are methods to handle that. I won't talk in much detail about those today, but we do use filtering methods and things like that to reduce the noise. That doesn't change the scaling, but it does change the coefficient out in front, so you can still get, something like an order of magnitude improvement of that. One of the other challenges has to do with the statistics of distribution. So when you have a tail of a distribution, it becomes increasingly difficult to resolve that tail. It becomes very noisy out in the small representation part of the tail of the distribution. It's very challenging to model a wide range of space and time scales. This is fairly universally true for almost all physical phenomena, so it's not really specific to a particle model, but it's very difficult to model plasmas which may have many orders of magnitude, maybe as much as 10 to the 15th in terms of orders of magnitude in both time and space scales if you're looking at astrophysical phenomena. So that presents a big challenge, not just in particle simulation, but in all sorts of simulations of plasmas. And then finally, it can be compute and memory intensive. And so in particular, the memory intensity is maybe even a more recent phenomena. So a little bit of history. In the 1950s, people were playing around with particle models. In particular, Buneman, Dawson, and Birdsall were playing around with these models. But no one really quite knew how they would use these and what use they would be. And the thing that really changed this is in the 1960s. In the 1960s, and actually about 1959 is when he first presented it and then published it later, John Dawson showed that he could in fact predict the phenomena of Landau damping. Landau damping had not been observed in the laboratory at that point in time. So he actually predicted it using particle simulation. And think about that in the late 1950s. He was doing it with 1,000 particles. So he predicted the phenomena of Landau damping before the experimentalists found it, and what he showed gave them enough information to design experiments to detect Landau damping, which in fact agreed with his predictions. So that really launched particle simulation. It made, in particular, the U.S. Department of Energy, whose focus in that area was in magnetic fusion, made them realize that particle simulation may actually be a very valuable tool, and they started to put a lot of funding into developing the method through the 60s and early 70s. And so you can see from the history here in the 1960s, there was a community effort to grow this. And so people were using hundreds and thousands of particles. They weren't simulating anything realistic. They were just showing basic phenomena. They were looking at basic instabilities and basic collective effects, and essentially just convincing themselves that this model captured key physics. In the 1970s, the fundamentals were formalized, so the particle scheme was really designed and was written into a couple of books, in particular the Hockney and Eastwood textbook, and then also the Birdsall and Langdon textbook. Both captured a lot of the information on particle simulation at the time. In the 1980s, people started turning towards early device models, and in particular looking at bounded models that became of interest. And so, in addition to that, looking at simplified collisional models, so being able to add collisions so that the plasma with the input of electrical energy could sustain itself by ionization of a neutral background gas. And so in the early 90s, I was working with Birdsall at that time, and we hired as a postdoc Ian Morey out of a group out of Australia. Ian Morey was doing some collisional models in which he modeled ionization as a step function, the cross-section as a step function. We brought him to our lab, and we developed that into an energy-dependent cross-section and built it into a model in which we included differential cross-section and so forth. So we had a very complete model based on experimental measurements of those cross-sections. And so that model then became the basis for our device models. In the 1990s, we developed device models which included adding a realistic external circuit, so that allowed us to have the plasma interacting with impedances. Those impedances had reflections, had external currents and voltages and so forth. And so we were able to simulate quite realistic devices using that. In addition, the Monte Carlo collision model was further developed in the 90s, and I've listed some of the key publications here. The object-oriented method was developed, and that was really aimed at having plasma simulation codes that would live longer than the developer of the code. So the typical plasma simulation of those days was written by a graduate student, and when that graduate student graduated, that code went away, and the next student started writing their own new code. And so as a result of that, students were spending a great deal of their time rewriting the same core code, and then only to add maybe one additional model to that, which was the subject of their thesis. So that meant that they spent 3 years of their graduate career rewriting what others had done, and then maybe 1 year developing their own model and getting results on it. And so that led to essentially a limitation of the depth that we could go into in a graduate thesis in those days. And so our idea was to develop an object-oriented model which would be largely independent of the developer. It would be very encapsulated, so different pieces of the model could be worked on by different people, and they wouldn't have to understand everything about the entire model in order to make any modification. And so that scheme was largely successful, and so those models that I'll show later today hopefully are based on that object-oriented scheme. And many of the national labs in the U.S. have also adopted C++ and object-oriented coding to develop their models, which are largely team efforts and largely have to outlive the key developers. And then in the 2000s, we moved into a parallel. We moved into developing more realistic boundary conditions, conformal boundaries, hybrid models using fluid and particle hybrids, for example, to try to improve the ability to address timescales, the ability to better address distribution functions. And then also GPUs, graphical processing units, for use as a parallel processing implement were also developed. In applications, these have been applied to a wide range of areas. I'm not going to go through all these, but you can see that they span the range from low temperature plasmas for materials processing, thrusters, and lighting, up to high temperature plasmas for fusion. They span from very non-neutral plasmas for beams and microwave sources and accelerator physics to very neutral plasmas where we're looking at, for example, a low temperature plasma processing with a neutralized plasma. So you can see a broad range, including basic physics as well. Okay, so a little bit about the model itself, and we'll just go through this very briefly, and then we'll try to get to the simulation part. And I should keep track of time here because I don't see a timepiece anywhere. Okay. Okay, so the essence of the particle and cell model is that we have particles which live in a continuum space. So these are Lagrangian particles. They can take on a continuum of positions, a continuum of velocities. And then we have fields which live in a Lagrangian space, in an Eulerian space on a mesh. And so these fields have to interact with the particles in some way, and so that's where a lot of the magic comes from, and that's where a lot of the filtering and other effects that we can get to improve the noise scaling come from. And so you can see in this model, in this illustration that I've shown here, if I can figure out which thing is the right. There we go. So in this model, we have continuum particles. This is just a section of a mesh, and we may have, for example, at nodes of the mesh, things like the space charge density, the current density, and the electric and magnetic field defined either at these nodes or somewhere along this mesh. And the particles then can move in this space, and the fields are typically always located at those same locations and computed repeatedly. So the overall PIC scheme really looks like this. So if we just start at some arbitrary place where we say we have particles and fields as an initial condition, we can then take those fields from the nodes of that mesh that I just showed and then calculate an approximation of those fields at the continuum location of the particle. And so if we can get that, we can then estimate the forces of those fields on the particle. We can use those forces in the equations of motion to advance the velocity and advance the position. And I'll show some of the algorithms we use to do that in particular. But essentially we're going from the fields to get a force, from the force to advance the velocity, and from the velocity to advance the position. And then we might take a look at the particle's position with respect to boundary conditions and determine if they've impacted a boundary or if they've otherwise interacted with something else. And we may also add a collisional model so that we check if the particles have interacted with a background gas, if they've ionized or excited the gas, and so on. And so then once we've resolved any of that, the collision, for example, would modify the velocity of the particle. It may create new particles if it's ionization. It may remove particles if it were recombination, and so on. Then we take those particles, their positions and their velocities, and we use those positions and velocities to create a charge density and a current density, and again calculate that on the mesh at those predefined locations on the mesh. So we go from positions and velocities to charge density and current density. And then using the charge density and current density in Maxwell's equations or in the electrostatic limit in Poisson's equation, we can then compute the new fields, the new electric and magnetic fields arising from this system. So this is the set of equations of motion that we solve. So you can see the standard Newton-Lorentz equation, and you can see also the relationship between position and velocity here. And this gamma is just the typical Lorentz factor defined for relativistic particles. So we typically make a change of variables, and instead of keeping the velocity v, which becomes very challenging for relativistic particles because of round-off error, we may have particles with 2.99 to many significant figures times 10 to the 8th power as their velocity, but in fact their energy can be dramatically different, and it's very hard to represent that. But it's much easier to represent if you calculate gamma times v. And so we then discretize this using what's called the leapfrog integrator. And the leapfrog integrator is named that way because, in fact, we stagger either the velocities or the momentum, the relativistic momentum, by half a step from the positions. And so using the positions and velocities staggered in this half-step fashion, we can discretize like this, and it becomes second-order accurate. And it also allows us to calculate this without storing intermediate values or storing old values, as you might have to do if you were solving, for example, a Runge-Kutta scheme or a multi-step scheme. This scheme lets you have a second-order accurate scheme with very few operations and minimal storage. And in fact, you'll find that PIC people really shave this down and try to find the least number of operations they possibly can, because remember, we're going to end up pushing millions or even billions of particles per time step. So we want to make the calculation per particle as efficient as we possibly can. And so this scheme is stable for time steps in which the product of the plasma frequency times the time step is less than 2. I won't show you the mathematics for that, although I have a slide for that, but it's easily derivable. And in fact, you can find it if you look in my, do I have it here? At the end, I'll have my review paper, which is published in Controlled Fusion and Plasma Physics in 2005. In that review paper, a lot of the details behind what I'm talking about are explained in a lot of detail. And you'll also find some of these details in the Birdsall and Langdon text. This is the so-called Boris push. J. Boris never published this in a journal, so it only lives in the proceedings of the fourth numerical simulation of plasmas conference in 1970, and I think I have one of about 4 copies left in the world, but in any case, for whatever reason, he never published it. But this is an incredibly clever scheme in which he split the particle push up into an advance for the electric field and a rotation for the magnetic field, and then another half advance for the electric field. This retains the second order accuracy of the method, but the really important thing that it achieves is it ensures that the rotation due to the magnetic field can add no energy to the particle. So for people who are studying magnetized plasma, this is an absolutely crucial result, because what it means is you can take as large of a time step as you want with respect to the gyro frequency, for example, and you will not modify the energy of the particle. All of the error shows up in the gyro phase. So that means that you're making errors in the gyro phase, which may or may not be particularly crucial to you. If you're in the middle of in the core of a tokamak plasma, the gyro phase is probably not particularly important, whereas if you're near a scrape-off layer, maybe that does become somewhat important. But in any case, this is a significant advance because for many strongly magnetized plasmas, that gyro frequency is a really difficult limit on the time step. It really forces you to have a very small time step if you otherwise have to resolve it. And this ensures that, for example, a particle gyrating in a magnetic field can gyrate in that field indefinitely and not spiral out or spiral in. Its energy won't change at all. So this is actually a very important advance. And this is the stability I talked about. I'm not going to go through the details of this, but you can see that in about 5 lines you can derive the stability. This is a cylindrical coordinates model in which we can do a rotation of a Cartesian frame to get some cylindrical coordinates. Again, this is the particle and cell community looking to avoid extra calculations. If we don't do this Cartesian rotated frame, we have to then solve for angular momentum and make sure that we conserve angular momentum, which adds additional equations and adds additional operations. So we're always looking for ways to reduce the number of operations. For electrostatic simulations, remember we said we solved the fields on a mesh, and so this is the mesh for electrostatic problems where we have the charge density defined on the nodes of the mesh as well as the potential defined on the nodes of the mesh. And so we can write this as Poisson's equation, and we can use a center difference. This is how it looks in one dimension, and the center difference is second order accurate. This particular implementation assumes a uniformly spaced mesh. If it's non-uniform, that introduces a first order error term. And I have a slide later which shows that error term is small if the change from node to node is, from mesh to mesh is gradual, so you don't make big changes in the cell size, then you can retain that second order accuracy. Boundary conditions are a very crucial part of applying this methodology to plasma devices. In the early days of plasma simulation, everyone looked at periodic plasmas. It was all infinite and periodic. And so in the late 80s, early 90s, we really started taking a hard look at doing plasma devices and including real boundary conditions, probes, and so forth, real driving terms to the plasma. So in order to do that, you have to consider the surface charge effects, the interaction of surface charges with the plasma. And this is just basic electromagnetic theory. If you bring a charge close to a boundary, that generates an image charge in the boundary, and we have to keep track of both the image charges and the free charges and the voltage on the boundary, depending on how that boundary is connected to ground. Its voltage may change as that image charge appears on the boundary. So we have to consider all of that information as we're doing this. This is the non-uniform mesh. I won't go through the details of this. You can read about this in the review paper. And so this is a solution for multiple boundary conditions. And this is really in order to have multiple driven boundaries or multiple absorbing boundaries in a simulation, and to be able to do that. And this was done by Vahedi, who was a graduate student in our group at Berkeley and graduated in the mid-90s. Electromagnetic fields are similar to the electrostatic fields. Now we have to consider also time-dependent magnetic fields self-consistently. So we end up, in this case, defining the fields along the edges for the electric field and along the faces, normal to the faces for the magnetic field. And so again, this allows us to do this leapfrog-like scheme. It allows us to write a finite difference for Maxwell's equations in which we do a center difference for all the spatial derivatives. And so you can see this center difference. In fact, you'll notice that the time step is also offset by half a time step for the magnetic field versus the electric field. So that allows us to do the second order accurate method in time. But you'll also notice that the spatial differences are offset by half a cell as well. And so you can see that both for magnetic and electric fields, and then we also use the constitutive relationships here. This method generates second order accuracy, again, for uniformly spaced mesh. And also we take care of Gauss's law and the divergence-free magnetic field. And if we have those satisfied at t equals 0, solving it using this scheme ensures that it will remain satisfied going forward if you use a charge-conserving scheme for weighting the currents. So the solution of the wave equation is dispersive. That means that waves propagate at speeds which depend on the frequency of those waves. So that's a numerical dispersion. It's not physical. That's a numerical dispersion. So you can see the exact solution is this light blue line. And in fact, in this scheme of equations, if we choose the time step and space step such that c delta t over delta x is exactly 1, we get the answer exactly right. It's not always possible or convenient to choose that time and space scale, however. So as a result of that, if we choose something in which the time and space scale is less, you can see the dispersion turns over, and the propagation speed for long wavelengths or high frequencies really turns over at that high end of the scheme significantly. If we're down in this region, however, we're not much affected by it. So as long as we operate where the physics we care about is down here, we should be okay. However, if we have a time and space scale such that c delta t is bigger than 1, c delta t over delta x rather is bigger than 1, you can see that we have still a phase difference shown here, but then there's an imaginary part. This is the imaginary part plotted here, and that represents a growing instability. That's a numerical instability which you'll recognize as the classical Courant Friedrich Louis instability. And this instability is rapidly growing. You won't mistake it for physics because it will generate overflows in a digital computer in about 10, 15 time steps. So it really grows very dramatically. And so lastly, I'll talk a little bit about coupling particles to fields. And so colors didn't come out so well here, but the essence of coupling particles to fields comes from this so-called shape function. So the particles are truly point particles, but we weight them to the mesh in such a way that they appear to have a shape. So if we sit on a mesh node and we watch a particle come sweeping by, and we measure the current on this mesh node as the particle comes from infinity and comes by, we'll see shapes that look like this. So the simplest shape we might choose would be whenever the particle is within half a cell of the mesh node, we contribute all of the charge to that node, and when it's farther than half a cell, we contribute no charge. So that would mean that as it approaches the cell, it has a charge density on this node of 0. When it gets within half a cell, it jumps up to 1 in normalized units. And then when it gets half a cell away, it again jumps down to 0. So we see that as a square pulse as that particle comes by. As you can imagine, if we Fourier decompose that square pulse, we have a lot of high frequencies, and that leads to a lot of noise in the system, and that noise is, of course, detrimental to the physics that we're trying to study. Now, we might choose a higher order method. The next higher order method we might choose would be a linear weighting, so that when a particle sits between two cells, we linearly weight its charge according to its distance from the nodes of that cell that it sits inside. So that means that as it approaches, again, from far away, as it gets within one cell, its charge linearly ramps up until when it sits right on top of the node, and all of its charge sits on the node. And then as it moves away from the cell, it linearly ramps down to 0 when it gets to be 1 delta x away. So that's the so-called linear weighting, and that gives a tent function. And that sort of triangle function has somewhat reduced noise properties, and so that's actually typically the most common function used in particle models. But we can go to higher order, we can use parabolic functions, and we can use third order splines and so forth, and higher order. Each of those higher orders, of course, involves additional expense, and remember you have to do this weighting twice per time step per particle. So that means if you have 1 billion particles, you have to do this 2 billion times per time step, so it has to be fast. If it's not fast, it's really going to impact the cost of the simulation. And then I'm going to skip through this. This really has to do with the accumulation of charge and numerical heating. This is maybe a more advanced topic. This is the current weighting scheme that we use for electromagnetic systems, and so it's quite similar in nature to the electrostatic scheme that I just described, but this is to weight the current density, and so the current density has a weighting which is 1 order lower in the direction of propagation compared to the transverse direction in order to be charge conserving, so it agrees with the charge density weighting. Okay, so I'm not going to go through these advances in detail, but maybe I'll just say a few words about them, and then we'll get on to the simulation part, hopefully, if the computer will oblige us. Okay, so here we have a general weighting scheme, and this was really devised in order to correct some systematic errors in the particle weighting that I just described. So this scheme is general for any coordinate system and any particle weighting scheme. External circuit model is a model that was developed to include realistic circuits, which can include resistance, inductance, capacitance, and so forth in the external circuit in various combinations. And in fact, researchers have even hooked up particle and cell models to SPICE, which is, if you're an electrical engineer, SPICE is a circuit simulator that can handle thousands or tens of thousands of nodes in a circuit. And people have hooked those up to particle simulation methods to simulate very complicated schemes. The Monte Carlo collision model allows us to model background gas interaction, so both atomic and molecular collisions can be included. Coulomb collision models allow modeling of the close-in Coulomb collision. So remember, in the particle and cell scheme, the Coulomb collision is not modeled directly. It's modeled through this interaction with the mesh. So as a result of that, we actually are quite accurate for simulating Coulomb's law for particles at a distance bigger than 1 cell. But for particles within 1 cell, the part of the charge is actually missed because of that weighting scheme that we described. And so as a result of that, the close-in Coulomb collision operator is underrepresented. So that Coulomb force is underrepresented in the standard PIC scheme. Now, there are various things we can do to correct that. We can essentially look at all the particles within a cell and do a specific calculation to add that term back in, but that's very expensive to do. But people have devised many other schemes to handle that. Subcycling schemes allow us to run different parts of the solution at different time scales. So we might have a very fast time scale for the electromagnetic fields. We might have a slightly slower time scale for the electrons and a much slower time scale for the ions, for example. And so we could run each of those on their own separate time scale and synchronize those. And as long as we do that carefully, we can get a higher performance out of that. Some surface interaction models such as secondary emission, sputtering, desorption of gases, and so on. So we've developed models for many realistic things like that. I talked earlier about noise control schemes. These are largely filtering schemes, and so we have some pretty diverse set of filtering schemes applied to this, that some of which come out of the signal processing community. So those are very useful. Radiation transport, we've looked at, for example, transport of radiative states and optical emissions out of a plasma, including interactions with a background gas to get Larmor broadening, and also interaction with, depending on the velocity of the particles, to get Doppler shifting, so that, for example, if we're studying the emissions from a fluorescent lamp, we can get both of those, both the Doppler shift and the Larmor broadening correct in terms of getting the set of wavelengths out of the system. So also high-performance computing has become an important part of this. As you've probably noticed, I've mentioned many times performance issues and challenges, and so high-performance computing has been one answer to many of those challenges. And so I'm going to stop there and switch over to the simulation if we're fortunate enough. So let's see if I can get that to come up. So I think I have to restart this. Here it is. That doesn't look encouraging, does it? Okay. Oh, okay. Aha, maybe it'll work. And so this is the virtual machine that you can actually download from the MSU website. Okay, so let's see. Okay, good. So this may just work. We'll see. Okay, so let's take a look at some 1D models first to keep this simple. And so I'm going to run a code called xpdp1. Where am I? So I apologize. I had all this set up before, but because we had to reboot, we had to. Okay, so let me start off by showing you a simulation in which I have a one-dimensional diode. So this is let's say, 2 electrodes and with only one dimension of simulation, so it's infinite in the transverse dimensions. So between these 2 electrodes, we will load some particles. What is that? We'll ignore it, see what happens. So we'll load between those some electrons uniformly, and we'll also load some immobile ions uniformly, and we'll look at sheath formation due to the finite mass of those electrons. The ions won't move, so in fact that sheath will act like it's an infinite mass ratio sheath. Okay. So this is, let me use this guy instead. Okay, so this is the control panel for the simulation. And you can see a huge list of diagnostics. In fact, let me put the diagnostics here and we'll expand the list a bit. So you can see that these codes have a tremendous number of diagnostics. You don't want to block the control panel. And so you should think of these diagnostics as being like probes that you can look at your plasma. So let's take a look at what we have here first. And so I said before we have electrons loaded uniformly. Good, that's showing up well. And so you can see these are the electrons loaded uniformly in this system. And you probably can't read this, but this is a 5 centimeter long system in X. And the velocities go between 2 times 10 to the 6 to minus 2 times 10 to the 6th. And so this is essentially a Maxwell-Boltzmann distribution as the initial conditions. The ions aren't shown because they're uniformly distributed and immobile, so they won't do anything interesting. However, the electrons will be very interesting, and in particular, we can look at their density profile. And so this initial density profile, don't be too disturbed by it. It's the initial condition. And this is beyond, this goes from 10 to the 14th to 10 to the 14th right now. As soon as I take a step, that will have a better range. And let's see, I also want to show potential here. Okay. So if I run this, what you're going to see is you're going to see these electrons, this top half, there's a 0 tick mark here. So the top half are moving to the right, the bottom half are moving to the left, and you'll see this top half hit the surface here and be depleted, and over here these will hit the surface and be depleted, and we'll see the potential rise. The electrodes at each wall are grounded, so they'll remain at 0, but we'll see the center, as the electrons are lost, the center will become net positive, so the potential will rise up. And it's going to happen pretty fast, but there it goes. So you can see the particles being scraped off on the edges here, and you can see the sheath being formed here. And you can see here the density, you can see the profile of the sheath in this density, and you can see the oscillatory nature of this plasma. And this is really ringing because the initial condition was obviously not the right condition, so there's an inertial effect. There's no damping in this system because there's no loss. If I wanted to add loss to the system, I could add, for example, a very low density of background gas, and collisionally that would damp some of that residual energy. Or I could add an external circuit with a small resistor in it, and that resistor would then slowly heat up and take out some of that energy, and that ringing would decrease. Okay, so you can see that nothing is changing now. This is going to stay like this indefinitely. This is settled down to about 10 to the 14th per meter cubed in density, and you can see the potential ringing is still going on pretty regularly, and you can see that we're not losing many particles anymore. We've formed the sheath in terms of this simulation. So now let's change this to look at a model, and this is going to be a tricky part. I had set this up before so that I had a steady state solution. I'm going to try to recover that, but I'm not positive it will work. We will see. What is it called? RF. So it thinks it worked, or does it? Let's see. Nope, it didn't work. Okay, well anyway, I'll start this from t equals 0. This is a very similar case, but the differences between this case are those electrodes at the end, instead of being grounded, held at 0 voltage. Now the left electrode, let me bring up the picture of the diode. The left electrode will now be held at, will be driven at, I think, 500 volts. So this is a driven system. I want that seems like a bad sign that I don't have particles. Yep. All right, let's restart that without the save file. Okay. Okay, so this is the initial condition in which we've loaded a uniform plasma. We're looking at the velocity in the x direction versus the position in the x direction. This is a 10 centimeter gap. And so you can see in this 10 centimeter gap, these are the electrons and these are the ions. And the ions are not properly scaled. Okay, and so we have the electrons and ions shown. We can also look at the potential in this case as we did before. And as soon as I take a step, that'll fix. So remember, this is a case where the left electrode is driven. The right electrode is held at 0, and this will oscillate at plus and minus 500 volts. And that's driven at 13.56 megahertz. And this is a real mass ratio of argon, and it also has the collision cross-sections of argon. I've forgotten now the gas pressure, but let's take a look at the gas pressure. Gas pressure in this case is, let's see if I can find it. There we go. So the gas pressure in this case is 50 millitorr. Well, that's lower than I thought. But anyway, it's 50 millitorr, so it's a relatively low pressure case. So let's let this run, and you'll see the similar sheath formation, but now you're going to see a slightly different behavior. Let me fix this scale. So what you're seeing here is you're seeing the electron sheath form as it did before, but now you're seeing the ions being accelerated into the sheath. And so these ions are mobile, even though they have an argon mass ratio. Because in the electron sheath, we have this large voltage drop, which oscillates from side to side, you'll notice. So the voltage drop moves from side to side, and it alternately accelerates ions in each direction. Now the ions are also collisional. The electrons have scattering collisions, they have ionization and excitation collisions, and the ions have charge exchange and scattering collisions as well. So that's why you see the ions fanning out. We can look at lots of different diagnostics here that might be interesting. We can look at things like how we're approaching steady state. I happen to know this thing takes about 50 microseconds or more to get to steady state, so we're far from that. We haven't even gone a microsecond yet. We're not going to sit and wait for that. I had that prepared before, but we had to restart, so we couldn't keep that shown. Let's see, I think I do want to show maybe some information. We have lots of different things. You'll see time average quantities. So at time average is to show you the density over a time average and things like that. You can look at things like the number as a function of time. This will tell us how it's approaching equilibrium. So here we see the number as a function of time. We can look at things that are time history. So we can look at, for example, the potential. It wants me to stop it because it's running so fast it doesn't have time to read keystrokes. We can look at the potential at the center of the system as a function of time. We have lots of things that show us information about the collisions. So if we want to see where the ionization events are occurring, we can look at that. So you can see the ionization events are occurring primarily near the edges, and in fact that will get more dominant. We'll see these two edges because this is a low pressure discharge, so at low pressures stochastic heating near the sheath edge is the most important part. So you can see that through the ionization. The excitation, this is the rate of ionization as a function of position. So you can see right near the edges of the sheath is where we have two peaks. We can also look at the heating profile, so we can look at where the energy being dumped into the system. This is a calculation based on J.E. So you can see in this picture of J.E, this is the energy absorbed by the ions. This is the zero line in the center. And so you can see the ions are being accelerated only in the sheaths, and that's where they're gaining energy. The electrons are being accelerated really at the sheath edge. There's a little bit of ohmic heating in the center, and this ohmic heating is the result of a net electric field through the center, which is slowly oscillating, and so the electrons are being collisionally heated through that. But the stochastic heating is more of a collisionless heating effect. And so this stochastic heating was in fact largely articulated through the use of simulation by Lieberman and Godiak and others. And so this was one of the main, in fact this code that you're looking at was one of the main tools they used to describe this phenomena. So you can see many other things. You can change the scales of all these things. We can actually treat this like it's an experiment. So if I want to look at, for example, a measurement here, I can ask it the question, what is the value of this point? And you can see in this little window down below, down here, whenever I click on a point, it'll update the X and Y values according to these scales on it. So if I click here, for example, it'll update the X and Y values according to that. So I can take measurements off of these graphs and so on. So so that's why I call it sort of a computer plasma laboratory, is you can do these kind of things. You can really look inside your plasma and see what's happening. So let me move on from this because I know we're running out of time here. I'd like to show a couple of 2D simulations as well. So this is a code called XUPIC, and the XUPIC code is a two-dimensional code. Let's see, I think I'll show maybe XUPIC can handle both Cartesian and cylindrical coordinates. And it also can handle both electrostatic and electromagnetic, and it's fully relativistic as well. And so this is the first object-oriented particle in cell code from the mid-90s, still in use today. So let's start with maybe a hollow cathode. So this is a hollow cathode, and you can see the electrodes of the hollow cathode here. This is going to have, the electrode shown here, and then there's another electrode around here. So this piece is the hollow cathode area, and so typically how these work is we'll have both electrons and ions. You can see this blue is argons, and this is the electrons over here. And so both of those are sitting inside this hollow cathode region. This is the accelerating region, and so there's a bias voltage applied to this surface, which will extract the particles out. So you'll see these electrons will rapidly move to the right in that region, and in this region will generate a so-called hollow cathode discharge, which will be self-sustaining. It will give us a current which flows out through that accelerating region. So this is used in thrusters, it's used as an electron source, and so on. So you can see the electrons being accelerated rapidly to the right initially. And then you'll see also, I don't know if you can see that. I can actually also turn on a trace so you can better see how they're flowing. So now you can see where they're flowing. And so they're rapidly moving to the right. And I can also show, for example, the number of particles. And you'll see the number of particles initially decrease, and then it will begin to increase again. And we're not going to run this to steady state again. This is going to take many microseconds to get to a steady state. But you can see the sheaths building up in the electron region and so on. We have lots of diagnostics here again. In 2D, we can look at things like all the different velocity combinations. So we can look at it keeps making me stop to show the diagnostics. We can see the various velocities. This is velocity in the z direction versus the z coordinate. So you can see both electrons and ions on this scale, and you can see the electrons being accelerated up over here. And so this will essentially go on until we build up a much higher density discharge in this hollow cathode region. Most of the electrons and ions in this region will disappear. These electrons are only being held back by these ions. Once all these ions disappear, and they will slowly disappear, if I turn this trace on, you'll see that they're gradually being accelerated to the wall. So you can see that they are eventually leaving the system. But we're not going to simulate that to steady state because of time. Let's move on to klystron simulation. So for those of you who are familiar with vacuum electronics devices, a klystron is a vacuum electronics device in which we have a number of cavities surrounding a beam channel, and those cavities extract energy from that beam and generate microwave energy from that. And so this particular variant that I'll show is a relativistic klystron. You can see the outline of the device here. This is the radial direction, and this is the axial direction. And you can see these cavities. This is a figure of rotation. So this is the axis of symmetry. And so these cavities are essentially circular annular cavities that go around the outside, and this is the beam channel. We'll send an annular beam down here. That annular beam will interact with each of these cavities. It will ring up waves in this first cavity, and in fact, you can imagine if I sent a single electron down this system, that electron would also result in an image charge following along in this wall. But when that image charge gets to this gap, the image charge has to go around the outside of this cavity, meaning that it propagates much more slowly than this beam, than the electron transiting straight across this gap. And so as a result of that mismatch, we end up with energy being transferred to the cavity and electromagnetic modes, standing waves, building up in that cavity. And likewise, we'll get a similar effect here, and the beam will get bunched. So you can imagine as those particles pass by that cavity, the fields at that cavity will oscillate in direction, and they'll oscillate according to the dimensions of the cavity. We've set this up to oscillate at about 2 gigahertz. And so as those particles pass underneath it, some will be accelerating and some will be decelerating, and we'll end up with bunches. So if we had 2 different bunches, if we had evenly spaced particles, as they go in front of it, they'll end up in bunches like this, and those bunches will propagate down, and when they get to the second cavity, that energy, that potential energy of those bunches will be then transferred into that second cavity and turn into electromagnetic energy, which we can use an antenna to propagate out. So this is how radar systems are made. This type of device is the type of device used, for example, to accelerate particles in particle accelerators, typically as well. So this is a non-neutral device. So this is, I like to call these non-neutral plasmas, but of course they're not technically speaking plasmas. There is no quasi-neutrality here. There's only electrons. But nevertheless, we can look at maybe the electric field map. This is a map of the electric field. Let me take a step. This is a map of the electric fields. And so far there's a little beam coming in right here. You can see a little blue spot right here. There's a beam that's going to come in. It's relativistic. This is a 12 kiloamp beam at about 400 kilovolts. So this is a highly relativistic beam. It's gigawatts of power, and we're going to actually get gigawatts of power out of this. It's quite an efficient device. Let's see, in addition to this, let's look at the velocity phase space, and in particular the z velocity. And so there the beam goes, and you can see these are vectors of the electric field. You probably can't see the vectors, but I'll blow that up in a second. You can see the beam bunching here. This is velocity in the z direction versus z, and you can see some are speeding up and then some are slowing down. And if we look closely here, I can actually zoom in on this, like so, and you can see some of that bunching going on in that cavity. And if I go to this cavity, you'll see the bunching very clearly. So you can see those bunches come by, and some of the particles actually get slowed down so much that they turn around and go back. And you can see those particles going back here. Here's the 0 tick mark. So some of those particles give up so much of their energy that they actually turn around and go backwards. That actually reduces the efficiency of the device. That's a pretty low current density that's turning around and going back. Now if I look at the field vectors just under this, you can see the beam is passing by here, and you can see that it's being affected by oscillating fields, which are slowing it down and speeding it up. We can see that even more pronounced if we look over here. We can see those fields oscillating very strongly. And if I go and look at the cavity modes, for example, we can also see the fields in those cavity. You can see the cavity mode oscillating here. We can also look at the power output. And so I want pointing history for the output. So this is the output power of the cavity. It's at about 2 gigahertz, and you can see that the magnitude of the power is shown here. You probably can't read this, but this is about 3.7 gigawatts of peak power. So that's a pretty high power to extract for this klystron. So let's see, I can see that I'm a little bit over time, so I'm going to stop there and maybe take some questions.
Al igual que el martes, quisiera dar prioridad a los estudiantes. ¿Hay alguna pregunta de los estudiantes?
Oh, so how the hollow cathode works?
Yeah.
Sure. Let me bring that back up then. So you're asking me a physics question, correct? You don't want to know what, you want to know how the physics of a hollow cathode should work, right? Okay. Yeah, I can show you that. Okay, so again, this is a great tool for explaining things like this. So let's actually start it running so we can get maybe a little farther in on this. So this is a graph of the phase space. This is the R direction, and this is the Z direction. This is argon ions, and this is electrons. And so these are real mass ratios, so you can imagine that the sort of the velocity ratio of these particles goes something like the square root of the mass ratio. Okay, so assuming the same electric field, that they're being accelerated by the same electric field, their velocities should differ by their mass ratio. So that's a pretty large ratio for argon. So these guys are moving very slowly, and these guys are moving pretty quickly. I can actually show you the relative energies of each of those. So actually, we also have an average kinetic energy as a function of time. Sorry, it wants me to stop it to open these things. That doesn't make any sense. Okay, I don't know what's going on there. Let's see, let me show you through the velocity plot. So this is a plot of the velocity in the z direction versus the z coordinate. I can blow that up. And let's run it again. And so you can see the electrons being accelerated. Let me freeze the scale for you so it's not bouncing around. And then after I do that, I'll put the trace on so I can see it more clearly on my screen. So this is Vz versus Z. So you can see those electrons that are being accelerated. Those are the electrons being accelerated through this gap down here. So if I turn this trace on, you can see these guys being accelerated. This is their z velocity, so you can see that they're accelerating through that gap, and then they typically propagate out through this other side. And so we're getting some of them propagating out. For the moment, these electrons are being held back by the ions in this region. But if I run this long enough, the ions in this region will disappear, and then all these electrons will be swept out, and we'll only have electrons being accelerated through here. So these are only a transient condition. You'll notice that some electrons appear to come out of the wall. So the way the hollow cathode sustains itself is in this region, ions accelerate to the wall. Let's turn the trace on for the ions too. So ultimately we'll have these sheaths build up, and those sheaths will cause ions to accelerate to the wall up here. And when an ion hits the wall, it has some probability of generating a secondary electron. That secondary electron is then accelerated back through this sheath. It gains a lot of energy. That sheath may be hundreds of volts. It gains enough energy to have multiple ionizations. So as it accelerates back through and creates multiple ionizations, that builds up this density. And this density basically sits here and is gradually transported out through this accelerating gap. If we look at the fields in that accelerating gap, you'll see maybe a little bit better picture of how that works. I'll blow that up for you so you can see it a little better. So you can see the fields in this accelerating gap are pointing to the right. You probably still can't see that too well. But if I zoom in on the accelerating gap, now you can see electrons will be accelerated to the right. These are field vectors at each node, and the length of the vector describes the magnitude of the field, and the direction of the vector describes the magnitude of the direction. So you can see that the electrons are being accelerated out through this gap. Now if I go back to this larger device, along this entire surface, this region is the so-called hollow cathode region, and along this surface we have intense fields, for example, near the edge, which are the sheath fields. So the sheath fields basically point outward from the net positive plasma in the center to the electrodes, and the electrodes are ground in this case. And so what happens is the ions are accelerated out, they strike the wall, generate secondary electrons. Those electrons are accelerated back in and sustain the hollow cathode plasma by ionization. So that's what's going on there. So if we go back to maybe we can look at the map of, let's see, I don't have the map of the ionizations turned on here, unfortunately. But in any case, we can certainly let it run, and you'll see that plenty more ions are getting accelerated here. Whoops, that crashed. Okay. Anyway, I must have clicked on something wrong. Anyway, so that's roughly how the hollow cathode works. Did that answer your question?
Yeah, tracing is especially helpful.
Okay, good. Any other questions?
Well, I may have a question. Of course, for plasma applications, it's very important to take into account the chemistry. Have you included chemistry in any of your projects?
Yeah, so depends what you mean by chemistry. So we typically include atomic and molecular collisions. Now we include those both in the volume and on the surface. In a particle and cell model, there's a limit to how many different species and collisions you can follow. It becomes very expensive. We have another model, which I'll actually talk about tomorrow morning. So if you want to hear about the other model, it's a kinetic global model. And in the kinetic global model, it essentially is a zero-dimensional model. In that model, we can follow thousands of species and tens of thousands of reactions and still solve things in reasonable amounts of time. Many simulations take only minutes to solve there. But in particle and cell, we're really limited to tens of species and maybe 100 or so collision types.
Also, we have a group of astrophysicists who are very interested in this kind of simulations. All right.
Okay.
So good. Well, let's thank the speaker again.
So one last thing, if you'd like to download these codes or this virtual machine, you can download these from ptsg.egr.msu.edu. So that's PTSG means Plasma Theory and Simulation Group. EGR is engineering, and MSU is Michigan State University, and EDU is the U.S. domain name for education institutions.
Right. So maybe if you send it to me, I can publish it.
Okay, very good. I will do that.